Okay, then let's try to use an examples to show how we can establish the dynamics of the given low-body manipulators by following the two steps procedures of the Newton-Euler dynamics formulation methods. Okay, so in this example, we are going to consider a two-link low-body manipulators. Okay, and let's assume the effects of the gravities. Okay, and dynamics modeling problem is essentially trying to ask you to establish or to calculate how much torque tau 1, how much torque tau 2. Okay, tau 1 is the torque generated from the first joint, tau 2 is the torque generated from the second joint. Okay, so how much torque you need to generate in order to maintain or to keep the low-body manipulators to move with the joint 1 with the position at theta 1, joint 2 theta 2, and with the velocity theta 1 dot, theta 2 dot, and acceleration theta 1 double dot, and acceleration theta 2 double dot. Okay, so this is the objective or the problem of this example. And then let's see how we are going to apply the methods we talked about here before, to solve this problem. Okay, so before proceed to the two steps, right, outward and inward iterations, so we need to know what kind of information we already know, or what kind of initial values we need to know in order to proceed. Okay, so information, we need to list all the informations. So the first one is, of course, we need to know what is the mass, right? M1, M2. Okay, and another information is we need to know what is the inertia of the first link, inertia of the second link. Okay, so to simplify the problem in this example, we're going to assume this inertia of two links are both equals to 0. Okay. And we also assume, the center of the mass of the link 1 is located at the tip points of the first link. Center of the mass of the second link is located at the tip point of the second link is here, right? Okay. Good. And the length of the second link is here, is L2. The length of the first link is here, is L1. Okay. So L1, L2, the link length. Okay, so what else information we need to know? So we need to know what is the distance between the center of the mass. For example, center of the mass 1 is here, located here. What is the distance between this point and the origin of the reference frame 1? Okay, so we need to use this information when in the calculations of, if you look at the equations here, in the calculations of here, right? This one and this one, right? In the calculations of the acceleration of the center of the mass. Okay, so let's assume PC11 is equals to, right, so look at these examples over here, is equals to the length L1 along the x1 reference, and this x-axis. Okay, and PC22, okay, is equals to L2 along this axis, okay, x2 hat. Okay, so what else? So we also need to know how much force, right, you applied to the tip points of the manipulators. Okay, so this force would be, let's assume it would be let's assume it would be F3 equals to 0, and the moment applied to the tip point N3 will be equals to 0. Okay, and we also know, as we did before many times, the initial values, right, including the angular velocity, angular acceleration, right, of the universal reference frame, right, they are all equals to 0. Okay, so based on this information, then we can proceed to derive the dynamics of the manipulators. Okay, the step one, what we need to do is to figure out what is the acceleration, right? The VC acceleration of the center of the mass for link 1 and link 2, right? As long as we have this information, we can apply the last two equations, right? Using the Newton's law, second law, and Euler's formulations, physical laws, right? To figure out what is the summation of all the external force, and then we can proceed to the second steps. Okay, so step one, the outward iteration. Okay, so first information we need to know is omega, right? Let's assume I equals to 0. From here, I equals to 0. So omega 1 is the angular velocity of the first joint. Is omega 1 equals to the rotation matrix. Oh, another given information for this problem is of course the kinematics. Right? In the kinematics, we know what is the rotation matrix from the i's frame to the i+1 frame. Okay, and we also know what is the translation vectors, right? It's p, let's say it's pi+1i. All right. So suppose we all know all these informations, then let's do the angular velocities. Here is rotation matrix r1 0 omega 0 0 plus theta 1 dot. Okay, so this is the given information, right? From here, suppose you want the manipulators to follow the trajectory with the angular velocity theta 1 dot, right, equals to theta 1 dot, okay, along the z-axis. Okay, so for this quantity, you know that omega 0 is equals to 0. Okay, then we only have 0 0 theta 1 dot. The reason is that this z11 is equals to 0 0 1 along the z-axis. Okay. Okay, then the second equation, omega 1 derivative, the acceleration will be equals to the rotation matrix 1 0 omega 0 0 dot, right? Following the second equations, and then we plus r10 omega 0 0 cross products angular acceleration theta 1 dot along the z-axis is 0 0 1 plus 0 0 I1 double dot. Okay, then this one will be equals to what? So look at the first term, it will be equals to 0 because this term will be 0, because this term will be 0, all the second term will also equals to 0, and this term will end up with only 0 0 the last term, theta 1 double dot. All right, so again, remember that we ignore the gravity effects. Okay, so this is the some difference you may see, right, from this example and compared to the one you can see in the textbook. Okay, and in the textbook it also consider the effects of the gravity. So if you want to see how we can deal with the gravities, you may want to look in the textbook. But what I'm going to say here is that the gravity effects will be cause just a very minor changes to the results we're going to derive here. Okay, so this is for the angular velocity, angular acceleration for the joint 1. So the next one is the linear acceleration of the joint 1. It will be equal, right, to the next equations here. It will be equals to the rotation matrix 1 0 omega 0 0 derivative cross products p 1 0 plus angular velocity 0 0. So this capital omega here is equals to the small omega. Okay, just copy it from the textbook, but they should be consistent. Okay, so these two notations. Okay, omega 0 cross products, omega 0 cross products p10, and then plus linear velocity, linear acceleration, sorry, v00 dot. Okay, and okay, then we are going to calculate what is the results of this. So you can see that this term equals to 0, this term is equals to 0, and the linear velocity of the reference frame 0 will be also equals to 0. I forgot to write it down here also. It will be equals to 0, 0. Okay, so the whole thing over here will be equals to 0. Okay, next one is to calculate what is the acceleration of the center of the mass of the first link. So it will be c11 dot equals to, following the formulas right here, you will have omega 11 derivative cross products, the pc11, and then plus omega 11 cross products, omega 11 cross products pc11. Okay, and then plus v11 derivative. Right. Okay, then let's see what is the results of these calculations. Okay, omega 11 dot is what is here, is this one. Okay, be equals to 0 theta 1 double dot cross product. What is pc11? pc11 is given here, right? So it be equals to L1 0 0, right, along the x-axis. The x-axis is the vector 0 0 1, right? Then we can plus omega 11 0 0 theta 1 dot cross products theta 1 dot cross products pc11 again is L1 0 0. Okay, and then plus v11 dot will be equals to 0 from here. All right, good. 0. Okay, so now next step is we are going to do the cross products. So for this cross products, it will be equals to, if you still remember the formula, so the first elements over here will be equals to, okay, we ignore the first row and then do the cross products, it will be equals to 0. So second element here will be equals to, ignore the second row and do the cross products and then take the inverse. Okay, so it would be, so 0 0 times 0 will be 0 minus L1 times theta 1 double dot, and then don't forget about the inverse. Okay, so it will be in negative, not the inverse, negative, sorry. So negative 0 minus L1 theta 1 double dot. Okay, so in the last element it will be equals to, okay, ignore the last row, do the cross product, it will be equals to 0. Okay, and then plus 0 0 theta 1 dot cross products. So this result, so these cross products looks similar to the previous one, so we can quickly obtain the results as L1 theta 1 dot 0. Okay, so then you will have this equals to 0 L1 theta 1 double dot 0 plus, okay, another cross products we need to do. So what is the results of this cross product? So we ignore the first row, do the cross products. It will be negative L1 theta 1 dot square, right? Good. And the second element will be equals to, okay, ignore the second row, do the cross product, it will be 0. Last element will be, ignore the last row, do the cross product, it will be also equals to 0. So the final results will be simply just negative L1 theta 1 dot square, L1 theta 1 double dot, and 0. Okay, so this is for the acceleration of the center of the mass for the first link. And after that, what we can proceed is, okay, so up to this point we have already figured out the angular acceleration and linear acceleration for the first link. Okay, and the next step, of course, we want to know what is the corresponding information for the second link. Okay, so we do the whole procedures again. So let me try to save some space. Yeah. Okay, so for the second link, what we need to do is, okay, starting from the beginning, omega 22, right? So we need to calculate omega 22 first. So omega 22 for using the first equations here, okay. So now I would need to be equals to 1, right? So omega 22 for in the first equation, we have it equals to R21 rotation matrix times omega 11 and then plus 0 theta 2 dot. Okay, so this is the rotation velocity, okay, of the second joint. So this quantity will be equals to, okay, so in this case, different from the first link, in this case omega 11 is not a zero vector, okay, but it's from here, right? 0 theta 1 dot. And we need to know what is the rotation matrix R21. Okay, and this information can be obtained from the kinematics, okay, models. Okay, so now let me just give you the kinematics model. The rotation matrix R21 will be equals to C2 S2 0 minus S2C2 0 1. Okay, so this is the rotation matrix R21 and then times 0 theta 1 dot plus 0 theta 2 dot. So omega 11 is coming from here. Okay, so then the results, okay, so you multiply this out and then plus this one, the result gives you 0 theta 1 dot plus theta 2 dot. Okay, so this is for the angular acceleration, omega 22. So next one would be omega 22 dot, angular accelerations. Okay, so using the second formulas over here, we can have omega 22 dot equals to rotation matrix R21, right, times omega 11 derivative plus rotation matrix R21 omega 11 cross products, right? Cross products the 0 theta 2 dot. Okay, and then plus what? Plus 0 theta 2 double dot. Okay, so it'll be equals to, let's see. So rotation matrix R21 is the same as this one. Okay, so we use the same rotation matrix over here, but you need to multiply that with a different vector. It will be 0 theta 1 double dot. right? And then plus this is R21, okay, the same matrix. Okay, so and then plus R21, you use the same matrix, or you put the same matrix over here, times omega 1, it would be 0, 0, theta 1 dot. Okay, cross products. Cross products what? Cross products 0, 0, theta 2 dot, and then plus 0, 0, theta 2 double dot. Okay, then let's see how we can calculate these results. So the first term, rotation matrix times 0, 0, theta 1 double dot, it will be equals to 0, 0, theta 1 double dot plus R21 times the cross products of these two terms multiplied together will be equals to equals to 0. Let me double check. Okay, it will be equals to 0, 0, 0, and then plus 0, 0, theta 2 double dot. So the final results would be simply just 0, 0, theta 1 double dot plus theta 2 double dot. Alright, so this is the okay, so this is the angular acceleration for the second link. What is the next? The next one is the linear acceleration, okay, for the second link at omega 2 dot. It will be equals to rotation. If you look at the formulas over here, okay, so this formula, so it will be equals to rotation matrix R21 times omega 1 derivative cross products, right? Is omega 1 derivative cross products P12 plus omega 1 cross products over omega 1 cross products over P12 plus V11 derivative, V11 derivative, okay? So then it will be equals to, okay, rotation matrix C2 minus S2 0 S2 C2 0 0 0 1. Multiply the whole things over here would be omega 1 dot, it would be okay 1 dot from here. So it's 0 0 theta 1 dot. Is it theta 1 double dot? Cross products, the translation vectors, right, from the frame 1 to frame 2. So the translation vectors from frame 1 to frame 2 would be what? It would be the same, okay, so this is also in the information from the kinematics model. It would be this equals to L1 first one second, it will be equals to L1 0 0. Okay, so in this case then we can have omega 1 from the first iteration is 0 0 omega theta 1 dot, so it will be 0 0 theta 1 dot, and then cross products, same vector 0 theta 1 dot cross products L1 0 0. Okay, so the reason of the P21 is equals to L100 is coming from the kinematics models, right? And we have done these examples, exactly the same tooling manipulators in the previous classes. Okay, so I'm not going to explain more about how we obtain the PC21 here. But just remember this is coming from the same location as the rotation matrix R21, okay, the kinematics models. Okay, and then we can plus V11 dot here is equals to, what is the V11? Well, V11 dot here is here. So it will be equals to 0. That's simple. 0. Okay, so let's see what is the results here. So this would be C2 minus S2 0 S2 C2 0 0 0 1 times what? So for this one cross products, we can do what we can do. The first element, it will be equals to, okay, ignore the first row, do the cross products, it will be 0. Second row, it will be equal to ignore the second row, and negative over negative L1, negative is positive, it will be L1 theta 1 double dot. Last element will be 0, okay, and then plus 0 0 theta 1 dot cross products 0. So I'm going to quickly obtain these results, okay, so you can do the same exercise by practicing how you can do the cross products for two vectors. Okay, to save time, I'm just going to give you the results here. So then you can further have this matrix, okay, copy that from down to here, and then dot products what? So let's do the cross products for these things over here first. It will be equals to negative L1 theta 1 dot square 0 and 0. Okay, so it gives you negative L1 theta 1 dot square L1 theta 1 double dot from here and 0. Okay, and the final results would be, after you multiply the rotation matrix, the final results would be good. It would be L1 theta 1 double dot L1 theta 1 double dot S2 minus L1 theta 1 dot square and C2. Okay, and the second element would be L1 theta 1 double dot C2 then plus L1 theta 1 dot square S2 and then 0. Okay, so this is the linear acceleration for the second link, and we are not done yet. What we need to have is what is the acceleration of the center of the mass instead of the link. Okay, so what we need to do is the omega C22 acceleration. Yeah, you need to calculate that, okay, by following the last, not the last, the next equations given right in the first step. So it will be equals to, in this case, it will be equals to omega 22 derivative cross products PC22 plus omega 22 cross products over omega 22 cross product PC22 plus V22 dot. Okay, so in this case it will be equals to what? What is omega 22 dot? It's from here, right? So it will be equals to 0, 0, theta 1 double dot plus theta 2 double dot, and then cross products over PC22 is a null vector, right, from here. As PC22 is equals to L2, 0, 0 along the x-axis. So that's the reason why I put L2 in the first element. Okay, and then plus, what is omega 22? Omega 22 is coming from here. It would be 0, 0, theta 1 dot plus theta 2 dot cross products over same vectors, theta 1 dot, theta 2 dot, cross products L2, 0, 0. Alright. And then plus V22 dot is this guy here. It would be L1 theta 1 double dot S2 minus L1 theta 1 dot square S, not S, is C2. And then L1 theta 1 double dot C2 plus L1 theta 1 dot square S2, 0. Okay, so then this one will be equals to, so then you do the cross product, it gives you 0, L2 theta 1 double dot plus theta 2 double dot 0 plus 0, 0 theta 1 dot theta 2 dot cross products over 0, L2 theta 1 dot plus theta 2 dot 0, and then plus this guy. Okay, so let's continue. Let's figure out what is the cross product of this guy here. It will be equals to negative L2 theta 1 dot plus theta 2 dot square and 0, 0. Okay, and then plus this guy, and then plus this guy. Okay, so finally you will end up with VC22 dot, the acceleration of the center of the mass of the second link. It would be equals to what? Be equals to negative L2 theta 1 dot plus theta 2 dot square plus L1 theta 1 double dot S2 minus L1 theta 1 dot square C2. Okay, and the second term is L2 theta 1 double dot plus theta 2 double dot plus L1 theta 1 double dot C2 plus L1 theta 1 dot square S2, and the last term will be 0. Okay, so up to this point we have figured out what is the acceleration of the center of the mass of the second link. And the next step, what we can do is we can try to apply the last two equations here, okay, to derive how much force and moments applied to each of the link. Okay, so following the equations here, we can figure out, okay, so F11 for the first link will be equals to the M1 times VC11 derivative. Okay, so what is VC11? VC11 is given here, right? You derive that over here. So what you need to do is to multiply M1 to each of the elements. You will have minus M1L1 theta 1 dot square m1l1 theta 1 double dot 0. And the moment n11 will be equals to inertia. Since you can note, observe that for the moments, okay, is always related to the inertia's I, right? And you already know that the inertia for each of the links are both equals to 0. Okay, so that's simple, right? So for each of the links, for both links, okay, so its inertia will be always equals to 0. So this one will be equals to n22 equals to 0. Okay, so what we need to have here is, okay, what is F22? External force applied to the second link. It will be equals to the M2 times VC22 dot. Then what is VC22? VC22 is here, this guy, okay? So F22 will be equals to M2 times VC22 dot equals to, okay, so let's write it down. M2 L1 theta 1 S2 minus M2 L1 theta 1 dot square C2 and then minus M2 L2 theta 1 dot plus theta 2 dot square and M2 L1 theta 1 C2 plus M2 L1 theta 1 dot S2 and then plus M2 L2 theta 1 double dot theta 2 double dot and 0. Okay, so up to this point, then we have finished the model of the dynamics through the outward iterations. And the second step is trying to do the inward iterations, right? Try to use the force information we established over here. Right? This is the force information, and this is another force information. Use these two information to proceed to the second steps iteration of the inwards directions. Okay, so let's see how we can do the inward iterations. Step 2. So step 2. So the inward iteration. Okay, so the inward iteration. So we're going to do F22 first. Okay, we'll start from the tip points and go back to the base frame. The reason is that the tip points force will always be given. Okay, it's F33. So let's do the small f, F22 here. So how much force you need to generate from the join 2. Okay, so it'll be equals to the first equations here. It will be equals to the rotation matrix times F3 plus F22, capital F22, okay? Is the rotation matrix R 21, right? It should be R21 or... So in this case, I is equals to 2. So R23, sorry. So R23 times F33 and then plus F22, capital F22. Right? Is this the equations tells you? Okay, so let's see what is the results, the values of this quantity. So the rotation matrix R22, let me just give you the results here, is equals to R23, sorry. R23 will be equals to C3 2 equals to 2 Oh, here we don't need to know what is the values of R22 because in this case, the F33 is value is equals to what? Equals to 0, right? So this is the information we have from the problem. So the tip point does not subject to any external force. So in this case, this term will go psi equals to 0. And then the final results of F22 would be simply just equals to capital F22. Exactly this one. Okay. And we also need to know what is the N22. Right? So N22 would be simply just following the second equations over here. Okay, so it be equals to let me try to copy these equations right here. No, bad idea. Try to copy these equations to here. Is N I equals to capital NII plus rotation matrix II plus 1 NI plus 1I plus 1